Okay, we're in section 10.1 here. We're talking about parametric curves, and these are just some famous parametric curves to know, really. And really, it's just practice using the calculator, okay? So go ahead and type these in and using the Windows settings and check and see that you would get the same picture, This would be important for section 10.2. The tractrix curve, so we did the involute of a circle. The tractrix curve has these parametric equations. That's hyperbolic functions, which you study in Calc 1. Okay, the word tractrix has been used in the study with horns and like concerts and stuff. The vertical axis here is an asymptote, okay? And the word tractrix means to pull or drag in Latin. And so one interpretation of this would be that, suppose that a dog owner takes his pet along as he goes for a walk down the y-axis here, and he's starting at the origin, and the dog is right here on a leash, okay, standing on the x-axis, some distance away from the owner, and the curve is traced out by the dog if he's like following his owner unwillingly. Like if he's constantly pulling the leash, keeping it tight, then he's going to get closer and closer to the y-axis but never get there, type thing. Okay. So let's see. Another curve to know is a cycloid. Okay, we'll do some things with cycloids in this section and the next section. Oops. There's the curve. Now, the word cycloid means was named by Galileo, and it was observed in the design for more accurate clocks. Like if you imagine, kind of an old time clock swing, where the pendulum is swinging back and forth, type thing. And so they studied this curve when they were, looking at creating clocks like that. Okay. But another interpretation of like where this curve is coming from is if you look at here's example 9 in the book. This is on page 666. The curve is you're following a circle as it's rolling along the x-axis, say, and there's a point P on the circle that's rolling along and it's tracing out this curve. Okay, as it's rolling along there. So that'd be one interpretation of where that curve is coming from. Okay. Now here's be sure that you use your calculator also, or that you know how to do that. Okay. So like if I were to type these equations into the calculator, I think I've already done that here. So there's t minus sine t and 1 minus cosine t. Okay, a is 1. Let's see, I'm on the window -8 to 8. So if I graph that curve, let's see, the t values are going from -pi to pi. So I think if I increase that, what if I go from -3 pi to 3 pi? Okay, then hit graph. Okay, there's that curve then. Okay, so again, for to see the complete graph on some of these, you might have to adjust the interval there for the t values. Okay, and let's see, the next one is an asteroid and a deltoid are kind of family members of the more common curve, which is called a hypocycloid. Okay, and what I mean by a hypocycloid is if you imagine a circle inside of another circle, there's a picture in the book here, and I'm on page 672. I got this bigger circle of radius A and this smaller circle inside of it of radius B. And if I watch the smaller circle roll along the bigger circle, it's creating a curve if I follow the point P. Okay, that is called a hypocycloid. In the next in epicycloid is another kind of curve, but that's where you have the circle on the outside of the bigger circle. Okay, and it's rolling along here and tracing out the curve, as you're following a point P, creating an epicycloid. Okay, so that's kind of where that curve is coming from there. And let's see, an asteroid would be where the radius of the smaller circle is 4 times as small as the radius of the bigger circle. Okay, if you have that, you'll create an asteroid curve. Okay, a smaller circle running around the inside of a bigger circle. And then you'll get a deltoid curve if the radius of the smaller circle running around the bigger circle is 3 times the or if it takes the radius 3 times the size of the radius of the bigger circle, then you'll get a deltoid type thing there. Okay, and then an epicycloid, like here's the more common type here. And there's a hypocycloid. Okay, but an epicycloid would be if I have a circle, and then there's a circle on the outside of that, and I'm following a point as the circle is rolling along the bigger circle there. Okay, and I can trace out these curves. Now a cardioid is going to be really important to us. Okay, that's going to be seen quite a bit in in this section and in the next section, actually all of chapter 10. And so we're going to talk about polar equations in 10.3 and 10.4. Okay, some of these curves are very common that you'll be able to see the polar equations for them. Okay, and I'll talk about that once we get there. But here's the parametric equations for a cardioid, and it'd be a different equation for if you had a polar equation. Okay, and again, like the reason why we're looking at all this stuff is because like if I want to find the area inside this curve, or if I want to find the distance that's been traced out, like it's sometimes easier for me to look at the parametric form or the polar form to get that. Okay, especially like when we're going to do in 10.4 we're going to do area and stuff like that. Okay, and so let's see, if A equals B. Okay, if if I have 2 circles that are the same size here, and the one on the right is rolling along the one on the center part there, and I'm following a point, then I create a cardioid. Okay, but if the circle in the center is a bigger circle than the one on the right, and in fact if the one on the right is if the radius is 2 times to get the one on the center there, okay, then I'm watching that roll along. Then I create a nephroid curve. Okay, and yeah, we'll do some things with these curves in the next section there. But here's the general form of that. Okay, and I'm selecting A and B values and X and Y, ranges, and graphing these curves. So, and again, the idea is for you to do the same thing. Like would you get this graph if A is 8 and B is 3, and you're looking at it in the window settings of -16 to 16. Okay. All right, now the last curve to know here is called the conchoids of Nicomedes, okay? And let's see, this is, trying to find, this is in the book somewhere. So this is named after the Greek scholar Nicomedes, and here it is on page 668. Okay, we got these curves here, and I basically just drew all of them here on this for you. But it's named after the Greek scholar Nicomedes, okay, and he called these conchoids because the shape of the outer branch kind of resembles a conch shell. Okay, all of these curves, except for when A is 0, have two branches, okay, a left branch and a right branch. Both the branches approach the vertical asymptote, x equals A, okay, so here's when A is 2. Okay, so both these branches are approaching x equals 2 from the left or the right, okay? Now, if A is less than -1, it's like if A is -2, both the branches are going to be smooth, okay? When we reach -1, the right branch is going to acquire a sharp turn, okay, called the cusp, okay? And then if A is some number that's between -1 and 0, the cusp is going to turn into a loop, okay? The bigger the loop, the smaller the A value, the closer that we are to 0, okay? So I'm approaching 0 from the left, and the opposite of that would happen on the right side there. So if A is some number bigger than 1, I got 2 smooth branches there, and of course the bigger the A value, the more smooth the branches are, the more distant they are. And when A is 1, the left branch here would have a sharp turn, and here's when A is getting smaller, closer to 0. So if A is between 0 and 1, I'm creating a little loop on the left branch, and that loop is going to be bigger there for when I'm getting closer and closer to 0. Okay, so again, all of these curves are very, very important in calculus. Okay, you'll definitely see them in probably 10.1 through 10.4, and when we'll look at the polar forms of these. A lot of these, coming up also. So, okay, all right. We'll go ahead and start the 10.2 then in the next video.